Okay. The share option is not available. Hello.
Hello.
Uh,
Yes,
the sharing option is not available.
I think share option is available at the downside. Will you see?
Yeah. It is there. It is written that share content, but I could not share anything.
Okay. So I'm contacting Mr. Atif.
Now it is available.
Okay. Thank you.
Thank you.
Now we have to start this session.
Is the
Third
screen?
of, yes.
Is
This
this,
is, yes. Visible.
okay.
Thank you, Professor V.N. Patel.
Yeah. Yes. Thank
So
you.
now today's lecture is lecture third of day 2, and the topic of the lecture is dynamic modeling of shaft bearing system for condition monitoring. And this lecture will be delivered by Professor V.N. Patel, and it is belongs to G Mechatronics Department, G.H. Patel College of Engineering and Technology, Vallabh Vidyanagar, Gujarat. And this program has been sponsored by ATAL Academy, and this faculty development program is organized by the Aligarh Muslim University. And now we have to welcome Professor V.N. Patel.
Thank you. Thank you.
Professor V.N. Patel is currently serving as Mechatronics Department at the level of Professor, G.H. Patel College of Engineering and Technology, Gujarat. He has obtained PhD degree from Indian Institute of Technology, Delhi, 2012, ME degree in Machine Design Discipline in 2001 from Sardar Patel University, and Bachelor of Engineering degree in Production Engineering from Shurastra University in 1996. Dr. Patel has a total of teaching experience of about 20 years at different levels such as assistant professor, associate professor, and professor. His research interests lie in dynamic modeling of vibration studies of single and multiple defects on rolling bearing elements, bearing races, modeling and analysis of cracked rotors, machine dynamics, and robotics. He has authored several publications in reputed journals like ASME Journal of Tribology, Journal of Measurement, Journal of Advances in Acoustics and Vibration. He has presented his work in various national and international conferences of repute. Dr. Patel has also got a patent to his credit. He has also served as a reviewer for many journals like Journal of Tribology, Journal of Measurement, Mechanism and Machine Theory, Applied Mathematics Modeling, and many more. Now we listen the lecture delivered by Professor V.N. Patel, and this lecture will benefit all of us.
Okay. Thank you.
Patel, sir.
Thank you, Yazin. Thank you for giving me chance for this. Okay, so my topic of today's lecture is dynamic modeling of shaft bearing system for condition monitoring. So that outline of the presentation, I am going to discuss about introduction of dynamic model and vibration, some fundamental related to dynamic model and vibration. Then how to model the rolling element bearings for condition monitoring especially. Then a little bit introductory part of mathematical model for two-disc rotor bearing system. So let us start with the introduction part. So as you know that decades ago, the design of machine and components were based on trial and error method. People were doing that trial and error method based on that knowledgeable craftsmanship. They just try something, then run it and learn from that one whether it is working well or not, is it reliable or not, and again make some correction and go back to the new solution. And later on, when that algebraic methods for analysis part is eliminated, and with introduction of that calculus methods, some documented methods has been computed, and based on that one, people have derived number of equations, and they have used the differential equations to understand that rate of change of the displacement, velocity, and other things, and based on that one, particular kind of design were done. And in today's industry, as you know that there is very little room or very little chances of the error, and we need optimize and cost effective production of the component, and more and maximum reliability is required, and durability of the component also matters. So here we cannot take any chance, and the trial and error method will not do much more. So in the today's research area, there are certain models have been developed and dynamic analysis have been done, but still there are these models and all these things are based on certain assumptions and approximation. That the develop nowadays there is development of fast data processing capabilities of the computer and like that. So more complex and more accurate model and detailed methodologies have been developed again, and which can be useful to study that defect detection and other dynamic analysis of the machine component in more detail with better accuracy. So that nowadays where earlier little bit room of error were there, those things have been removed, and nowadays number of even ready-made softwares are also available, which can be useful for defect detection as well as for dynamic modeling of the component. So faster data processing is also required, and the development of the softwares like MATLAB, Scilab, all these are providing data processing techniques, and even special tools of signal processing techniques are available in that one. So we can utilize those things for understanding dynamic characteristic of machine components. Why do we study this? Vibration is important for design engineer. Why should we study this vibration? So as a design engineer, when you are designing any component, so adjusting those physical parameter or dimensions of the mechanism or of the component in such a way that you can reach to desired level of that vibration amplitude, as well as you can design the component with a required natural frequency. Why do we need to design in a such a way? Because certain times you need to find out a working range of the machine. Working range, that means at which speed the machine should run so that the amplitude vibration amplitude can be decreased and it will not match with the resonance frequency of the component. So we will find out resonance frequency and natural frequencies of that machine component, so which will not match with that running speed of the machine. And when we want to design the components such a way that suppose we do have certain components are available with us and we have to arrange those components. So arrangement of those components, either it should be in parallel or series, which can affect the vibration response of the component. So by designing or by understanding the vibration or dynamic analysis of that one, all these things are possible. So it will be helpful in designing the new machine or analyzing the older one machine, and we can find out error in that also. So most of you are aware about vibration. So what is vibration? Actually, vibration is a to and fro motion completely by itself. Suppose this is its mean position of the bob, so it will move towards this direction. And once it is disturbed from here, if you leave from here, it will move in opposite direction. It will continue. This is the simple example. And as you know that when you are disturbing from its mean position, that potential energy will reach to its extreme value. When it reaches to the zero position or mean position, again that potential energy will convert into kinetic energy. Again that kinetic energy will convert into potential energy, and this will continue. These are the fundamentals behind the vibration, and it is change of motion and changing in energy. So all this part, most of you are aware about that. Suppose there is a spring mass system. Spring is at particular, if you are disturbing from here, it will move here. Then again it will go in reverse direction. Then it will go back to initial position. So based on this one, you can find out or you can draw its displacement diagram. And this particular figure, as you know, that harmonic motion x3, that can be defined as initial value and multiply with sinusoidal signal, and that omega will be its natural frequency of that particular vibrating system. So we can plot either its displacement, we can plot its velocity, and we can also plot its acceleration. So these are the fundamentals which you are knowing. And as you know that for any vibrating system, the main components of the systems are, it can be a mass of the system, it can be a spring element, it can be a damping of the system available in the particular system. So all these components, all three components, one of any two, that is possible source of energy, or it can be different energy behavior. Either it can store the energy supplied to it, or it will dissipate all the energy in form of heat like a damper. So spring will normally store the potential energy, the mass will store kinetic energy, while the damper will dissipate that energy in form of heat, like a, we are using like a friction will try to resist the motion and it will be in form of heat. So the spring element, so it, as we discussed that it, the potential energy is given by 1/2 of kx square, where k is the spring stiffness load per unit deformation, or load required per unit deformation. For different arrangement of the component, suppose road is under axial load, you can find out based on stress and strain, you can find out it stiffness value. Same way, suppose it is tapered rod, K can also be found out based on its diameter. Like a spring element, helical spring, you can find out value of spring stiffness. Suppose component is acting like a cantilever beam, you can find out that K equivalent for that also based on the value of its Young modulus, length, and value of I. That second mass moment of area or moment of inertia we are saying. And based same way for simply supported beam, there are number of components which I have not included. This is just introductory part of that, because already most of you are knowing about that spring elements and other things, just brushing up some fundamental. And same way the damper element in a damper will dissipate all energy and convert that mechanical energy into some thermal energy, or in form of release that energy in form of heat. And the damper force is directly proportional to relative velocity or of its two ends. The different kind of dampers which you may come across will be a viscous damper, Coulomb damper, or it can be a material or solid damping. And the equivalent damper can be derived, suppose there is a relative motion between two parallel surfaces, the equivalent C value can be derived. If it is like a dashpot, then based on that value of diameter, value of this length and distance or clearance, that C equivalent can be derived. Same way for column damping or frictional damping, we can find out C equivalent values. Then other component, important component is mass element. Mass element is describing that that is unrestricted or unrestricted body that resists application of external force, and that is inertia element in any dynamic system. So as we have discussed about that mass, it store that potential energy, and we can get it in different form of that. This is a replacing simple analysis can be done by converting to single spring mass system. So vibration analysis procedure, when we are doing any vibration analysis, what does it include? First step is deriving that mathematical model and finding out its free body diagram and other things. Then the second thing will be derivating of governing equations, will derive that governing equation based on the component or based on the availability of elements in that. Then we will find out the solution of that governing equation, and then we will interpret the result of that available result from that governing equations derived from the solution of governing equations. So why should we understand that, or why should we derive the mathematical model? What is importance of mathematical model? To understand the behavior of any mechanical system or to design the new machine, we can derive the mathematical model, and analysis of the any system or machine by method of classical mechanics is called as a derivation of or deriving the mathematical modeling. And to simplify that things, many complicated system can be understood, that dynamic behavior of the system can be understood by deriving simple mathematical model. You can find out its first natural frequency for analysis, and for some complicated and important class of the system like aerospace, automobile or packaging machinery, robotics, its 3D models are derived, and based on 3D model, we can find out that based on that one, we will find out its stiffness is of the component, what kind of damping is available there, and based on those analysis or based on those model, we will derive its that equations of motions, and we can solve those equation of motions. The simple thing, suppose there is a IC engine available like this way. Here, this is a flywheel of the engine. This is a cylinder. This is the piston moving inside the cylinder, and this is the crank that is connected with this flywheel. So suppose I want to find out simple mathematical model of this thing, we can take like this way. We will consider that this particularly flywheel is a rigid component and heavy mass. So we are assuming that there is a no movement of that one. So we can consider it as a rigid part. Then the second component, there is a crankshaft, that we can consider the stiffness of the crankshaft here, and at the end we can consider this particular piston and the crank is moving in particular direction, so we can consider it as a rotor. So here I have got that this particular value of I, then theta is one variable, then k is the stiffness. So we can derive I theta double dot plus k theta is equal to 0, because there is no additional force acting over here. So based on that particular system available, we can consider or we can derive some equivalent single degree of freedom model here. For better understanding or for more accuracy, we can increase number of degree of freedom. We can consider these as also a rotating part, and we can add some more constraint in that, and complex model can be derived, which can give the better result than this simple model. Same way, in this example is from SS Rao book. Here we can see that one rider is riding that uh, two-wheeler or a bike, so motorcycle, that simple model, single degree of model, we can derive that the stiffness is available for the struts will be considered as it is. The total mass of the rider and the bike can be considered as a lumped mass, and whatever the damping effect is available here due to the dashboard, that has been considered here. So this is the simplest model for this case. Then for better understanding, we can convert this thing into 2 degree of freedom system also by considering that mass of the vehicle and mass of the rider as a lumped mass, and mass of this two wheel as a separate part. And in between that one, whatever the stiffness part is available, we can take that struts as a stiffness over here, while the stiffness due to the rubber tire, that can be given separately. So this will be 2 degree of freedom system. So this is how we can convert that simple system into some single degree of freedom system or 2 degree of freedom system or more complicated, or even it can be increased more degree of freedom by separating out that mass of the vehicle and mass of the rider separately and adding that additional stiffnesses, it can be derived better way also. Then equation of the motion, how to solve those equation of motions. As you know that equation of motions can be solved by force equilibrium conditions or by means of energy methods. That I am not going in the detail because all of you are knowing about that. Suppose there is undamped free vibration system here. So for that one equation can be mx double dot plus kx is equal to 0. You can derive the equation. You can solve this equation by using MATLAB ODE solver. These results are based on that ODE solver. And here some typical equations where damper is used, and as you know that damped of free vibration, there is no additional force is acting. So you can derive that equation, and the solution of the equation using ODE can also provided by means of that, by using that MATLAB. You can also find out the frequency of that by using FFT function available in MATLAB. Same way, suppose there is a forced vibration, some additional force is acting over here. So the equations will be mx double dot plus kx plus cx dot is equal to f0 sine omega t. So here the vibration amplitude does not dissipated, but some continuous value is there. It depends on force applied and application of applied force. So this part is not zero, and this can be same way can be done for multiple degree of freedom system also. You can derive number of equations. Suppose there are three masses, so three equations are available. The relationship between mass 1 and 2 and whatever the spring constants or damping values are available, it can be derived in form of this matrices. Okay, now why should we study the dynamic model of rolling element bearing? Why I have selected this particular modeling of rolling element. This whatever the things I have discussed, I have moved little bit fast because those were the fundamentals and which were known to you. The dynamic modeling of rolling element bearing are important. Why? Because that wherever if you will see the major components or wherever you will go for rotating machine, majority of the bearings used in domestic or industrial machines are rolling element bearings. And if you rolling element bearings, assume that it can be a outer race, it can be an inner race, it is rolling elements, either it can be a balls or it can be a rollers, and all these balls are separated out by means of the cage. And what is importance of this thing, as the performance of any rotating machine depends on quality of bearings available in it. If there is a defect in the bearing, that will all definitely affect the performance of the machines and that domestic instrument also. Same way that bearings are manufactured with high precision and machine tools and passing through some strict quality control. Even though there can be a local defects or distributed defects. In that previous lectures, sir might discuss about all these things. What is local defect? What is distributed defect? The local defect like a pit, spalls, cracks, etc. are generated due to the manufacturing error or due to the fatigue or due to the plastic flow. So here I have separated out two things, local defects, and here these are distributed defect. And local defects are normally a dirt or dent or spalling, tree falsing and britling. All these are considered as a local defect, while distributed defect like a waviness, misalignment of the races, off size of rolling element, surface roughness, and manufacturing, and all these are considered as a distributed defect. So in today's lecture now onwards, I will discuss how to model all this, either it can be a local defect or distributed defect. How can we introduce this part in dynamic modeling so that we can understand the dynamic behavior of defective bearings? So these are some photographs of different kind of defects on the bond races, like due to the corrosion, due to the lubricant failure, and these are overheating or misalignment, and this is due to the overloading. This the surface roughness available. This is a distributed defect. This is outer race waviness available in that one. This is inner race waviness. Okay, so what happens if defect is available in any bearing? What can be the vibration response of that defective bearing? Suppose in this particular case, suppose a crack or defect is available on outer race of the bearing. As this particular rolling element come into contact with this defect here, so what will happen? It will generate impulse. As you know that as this particular element will come into contact with this defect, due to the change in the stiffness over here, it will create one kind of impulse. Or other way you can understand that when there is a ball will come in contact with this defect, it will create one impulse as a part of impact force. When this another element will come into contact with the same defect, because this cage is rotating in this particular direction, so when this particular ball will come into contact with this, another kind of impulse, another impulse will be generated. As the third ball will come into contact, this impulse will come into contact with this one and impulse is generated. Same way, this will be continuously. But here the important thing is that the time of this impulse generated will be a constant. It depends on geometry of the bearing and also depends on the speed of rotation of this particular cage. So this, if we are finding, if we do, we find out that time period between these ones. So 1 upon that time period, that will call us ball pass frequency of outer race. Same way, if there is a defect on inner race, same kind of impulses will be generated, but it will be different in nature. So that part also we'll discuss here. And if there is a waviness available on the ball bearing, then the ball will pass on this wave, so the ball will move in this particular direction, and the path will be generated will be a sinusoidal path. So you can design that thing, or we can design, or we can find out this dynamic model while ball is passing in this particular path. So as I said that, as if the defect is available on that outer race, it is the frequency provided or the time period of that impulse is generated. So reciprocal of that time period is ball pass frequency of outer race, which depends on number of balls, depends on rotating speed and the dimensions of the bearing, or that mean diameter of the bearing, ball diameter of the bearing. And same way it is if the defect is available on inner race, ball pass frequency of inner race is provided by this particular equation. And if the defect is available on the rolling element, then the impulse generated will be having the different time period and that frequency will be different. Same way that fundamental train frequency when ball is passing, that it will be provided by this particular equation. Now how to derive the governing equations and how to derive that equation of motion for different dynamic conditions. So while that defect come into contact with rolling element, different approaches have been adopted for dynamic modeling. The defects are modeled as a series of impulses that was given very first time was given by McFadden. Then that was better model was provided by Professor Tandon and his students Chaudhary sir, and they have given that lumped mass modeling. Then it was again refined by me and my professors, and again it was refined by my one of PhD student, that distribution mass modeling. So different things I will discuss here. All these different possibilities of models and different conditions I will discuss here. So defects, when defects are modeled as a series of impulses. So as I have shown in the figure, that when particular rolling element will come into contact with defect, it will generate one impulse. So when at time t is 0, suppose this impulse is generated. When another ball, the next rolling element will come into contact with the same defect, it will generate another kind of this impulse. So as that all the number of rolling elements will come into contact with this particular defect, this kind of impulses are generated. So ultimately it is a series of impulses. So it can be simply modeled by considering delta function. So at time t is equal to k times t time period of the defect. It depends, again this value depends on the availability of the defect, whether it is available on inner race or outer race of the bearing. And if t is equal to, at time t is equal to k times td, so that number of impulses are generated, and for 1 td, 2 td, like that you can have this series. So simply, if you want to understand the defect severity and other things, based on the type of the defect and depth of the defect or width of the defect, the magnitude will change. But this particular here, just now it is not considered. And if I will convert that the frequency analysis of this one, I will get that at 1 upon td time, I will get f is equal to at k times ft, I will get some frequency peaks in frequency domain. And this impulse series has been generated using the MATLAB function pulse train, in which you can generate this kind of series, and you can convert that frequency analysis of this also as based on 0.01. So it is 1 upon 0.01, 100 hertz is its frequency. So you can get that frequency impulse here. Same way, this one, as I said that in the last model available there, that amplitude were not concerned, but in actual condition, if you are considering that actual bearing, the impulse is having different amplitude because the load distribution of the bearing is different. Suppose downward force P is acting over here. In that case, some number of balls are under heavy loading condition, while remaining balls are not in heavy loading condition. So the distribution of the load is given by this particular way. So here this particular load, or that particular ball number 8, as in this one, is under heavy load. So the load acting is Q maximum over here, and for any condition we can derive that by Q phi. So if we want to find out actual amplitude of the defective impulse, then we have to multiply this particular load distribution, as here it is shown here between this point to this point. The load is varying, like using these equations we can find out that profile also. Here this is beginning of while the that a ball is entering the load zone, and the ball 2 is at when it moves out from the load zone. And if we will multiply these particular things with impulse train, so here suppose this particular impulse train, which is derived by using that delta function, when we will multiply with that loading condition, here. So ultimate, we can derive that Q value by using this one, or the impulse is generated due to the defect under load zone will be this one. Outside the load zone, actually the defect magnitude will be very less. So this is actually considered as a 0 by McFadden and Smith. And the another things, that while that defect is generated and the bearing may be under the housing, so there will be always there will be a transmission effect. So transmission effect can be again multiplied with providing some additional exponential function. If you multiply this thing with additional exponential function, so in time domain it is a dot product, but in frequency domain it will be a convolution. So that this particular things based on the bearing, we can derive this thing using the MATLAB also, and you can find out that frequency instead of that only impulse train, now it is multiply with that load zone, or considering that where the ball is, based on its location of the ball, the force acting on the ball changes, which can be given by this particular model. Suppose I have used the bearing number or bearing manufactured by SKF and bearing number BB1 B420206 for this particular bearing. This is its again a load distribution, and I have derive these particular things when it enter in this one. This is beginning of load zone. As the ball enter in the load zone, the load acting on that will move from beginning. When it reaches to the maximum one, then again it will reduce to 0 when it comes out from the load zone, like this one. For entering from this point, it reaches to the maximum, it will be 0 at this particular point. So you can use this equation to derive that condition or to find out loading condition. Now for this particular bearing, that suppose time response for inner race default as per this particular, based on that impulse train and this by multiplying its load zone, the defect detection or this particular defect has been derived or defects has been implemented for inner race defect, and its frequency response is provided here. So as you can know that whatever the time period between two impulses are there, that is available here as a part of BPFI. In case of inner race defect which rotates with shaft frequency, so along with that ones, that frequency FC and its harmonic available along with BPFI. So if the defect is designed for outer race, then along with that one, that available, these are the defect or that impulses due to the outer race defect, and the time period between two things, and one inverse of that will give you ball pass frequency of outer race. Then another approach which was used by Tandon sir and Chaudhary sir, that was lumped mass system. As we know that spring mass system, simply this is mass 1, this is considering shaft and inner race mass. Here that is a damping, stiffness produced by the shaft. Here there is outer race and the stiffness of outer race, and that bearing stiffnesses have been used considering linear stiffnesses, and some damping effect is used, while here the third mass is mass applied or the additional load applied to the bearing. So it is a lumped mass model, and equations were derived for this case like this way. This is simple mass matrix, damping matrix, and this is stiffness matrix. And for this one, the stiffnesses and other things used were a linear stiffnesses and This K2 bearing stiffness was derived based on the total load acting on that one, as we discussed this particular equation, and K delta raised to n part has been added over here, and value of K2 has been used in this particular matrix. Here this F1, F2, F3 are considered for consideration of defect. If defect is available, in that case value of Ft cannot be a 0. Here the impulse value of that for defect impulses have been provided by considering this way. Suppose defect is available on inner race, so while that ball come into contact with that particular defect, some particular impulse or the force function, rectangular or it can be a triangular or it can be a half sine wave. These kind of functions have been derived by them, and as a force function it can be given with particular frequency. So this frequency depends on location of that defect. If it is on inner race, then value of omega will be depending on BPFI. If it is on outer race, it depends on BPFO. If it is available on rolling element, it will be based on that. Here, these particular things which has been derived for different values. Here, these particular things, you can see that time domain response of inner race defect derived by these particular equations and using this F2 value for inner race defect, this kind of responses can be generated. And here, if we are considering that pulse shape is rectangular, forces are acting over there, then this kind of frequency response is available in that case, but these things are not that much clear. So if we are using that triangular shape, it will become better, and it will become best in case of this half sinusoid wave, or if you are considering that half sine wave as a force function, we will get better result in dynamic modeling. Now I have derived the things in more detail by considering distributed masses instead of considering that lumped mass system. Suppose this is the system under study. Here this is the bearing, test bearing, for which we will capture the vibrations, and we have derived the model for that one. This is the side view of this particular part. So more detail, the dynamic model here, the mass of the shaft is ms is shown over here. The stiffness of this particular part of the shaft is shown here, and the material damping of the shaft has been considered as CS. Then here, when the ball is in contact with inner race, whatever the stiffness is produced between inner race and the ball, that is KI for inner race. When that ball is in contact with outer race, the stiffness produced between that two, that is KI of outer race. That different stiffnesses have been given. So this particular model will provide better result than the lumped mass system and simple that impulse series. So here, how to derive that deflection of the ball. So total deflection of the ball is non-linear and given by Harris, that Q is equal to K stiffness and delta is deformation of the radial deformation of any rolling element, which is given by delta R, its deformation at the maximum one, and with cos phi, which when it changes its position, as we know that load distribution is different for different balls. So that value can be considered. This is for consideration of that diametral clearance. The ball position at any time t can be given by based on number of balls that or periphery is divided based on number of balls. Then it rotates with angular velocity of the cage, so that ball position can be changes with that. So omega c and t provide that one, and this is the initial position. So total displacement of the ball depends on displacement of the shaft and displacement of the ball into cos value in y direction, deformation or displacement of the shaft and displacement of the ball, and same way displacement or difference between ball and housing in x direction, displacement in y direction between ball and housing. So these components shows that its angular position, and this part is its radial clearance based on its position. So stiffness of the shaft has been derived by considering that moment and area moment method, and this part at which position I want to find out stiffness, I have considered that case. Suppose defective bearing is mounted over here, then I have to consider the stiffness of this part only. I have considered that one here. And in the model of that housing model has been designed by using that FVA modeling, and stiffness was found out by means of that ANSYS. The stiffness between ball and inner race Ki inner is given by this equation, Ki outer is given by this equation, and which includes the Young modulus. It depends on that Poisson's ratio, it depends on that deformation of the ball, it depends on the radial of curvature. And these are the material damping which is available in paper of Genta. I have used ready-made equation that suppose simulation of the local defect in that dynamic model. Suppose that this kind of defect is available on bearing. So this particular defect on outer race, defect 1, this is defect 2 on outer race. So when that ball come into contact with the defect, in impulse case, some impulses were considered, while in case of Tandon and paper, they have considered that rectangular or triangular force function or semi-sinusoidal force function. Here we have considered that when the ball will come into contact with the particular defect, that deformation or some additional deformation will be generated. That additional deformation can be calculated based on geometry of the bearing, ball size, ball positions, and when the ball will start to come in contact with the defect from this point to this point, the deformation also changes. So for outer race, when the ball is in defect zone, we will provide some additional deflection delta along with that, which was used for simple radial deformation. So total deformation will be deformation due to the load plus deformation due to this defect. And if the deformation is or that defect is available on inner race, some additional deformation will you can count based on this particular value of, and that it also depend on depth of the defect, size of the defect. As the size of the defect changes, the deformation also, the additional displacement also changes. So for rectangular defect, I have found out that this is the equation for rectangular defect. The additional deformation can be computed. Suppose it is a circular defect on inner race. Suppose like this way. So initially ball will come into contact at this corner, then it will move here, then it will reaches to the end of the contact, end of the defect. So it can be changing like this way. Suppose at initial position, this much part is inserted in that defect, then when it reaches over here, the total ball will be in contact with that one. When it moves out, it will be like that. So that value of the displacement varies, and it can be shown like this way. And when approaching to the defect, to the moving out of the defect, the displacement value changes. So type of the defect and size of the defect, based on that one, we can find out what will be the additional deflection. So total deflection will be considered at this part of the ball, and same way in the bearing. So if we want to derive the equation of the motion, this part will provide for the shaft masses and acceleration of that, stiffness of the shaft, then displacement, and this part is for contact of the ball and races, inner race. For balls, that will be for shaft part, and this is for contact of outer race and the ball. In X direction, in Y direction. So that deformation part will be considered here in both the cases. So effect of that can be available in its displacement diagram. So for the housing also, same part will be there. This one and this part, this is non-linear displacement, and it can be given in that form only directly here. So total deformation of the ball when it passes through the defect, it can be given for X direction deformation of the displacement of the shaft and ball in X direction, in Y direction, and this additional deformation is due to the presence of the defect. If defect is available, beta value will be 1, otherwise it will be 0. And same way for outer race. So the equations of motions when were solved by using MATLAB ODE function. So that here we need to provide certain initial values. We will require to find out bearing stiffnesses. We will require to find out ball positions, angular position of the defect. When that ball position and angular positions of the defect is same, some additional deformation should be added. That can be given by this beta ij is 0. That means it is not in defect zone. If beta ij is 1, or other way, if ball is in defect zone, beta ij value should be 1. So the vibration response of this actual system, which is available in IIT Delhi lab, in dynamics lab, we perform the experiment also to verify the results available from this dynamic model. So here the accelerometer is provided, which can capture the vibrations generated by this defect. If some additional vibrations are to be added, that can be added by means of this shaker, electromechanical shaker, for consideration of actual situation available in industry where additional vibrations are coming along with these bearing vibrations. So for this particular shaft bearing system, this particular figure provide the vibration response of the healthy bearing. Actually, these results are available or derived based on the equations or by solving the equations of motions which I discussed. When the ball is at this particular position, ball number 8 is at this particular position, there is a maximum amplitude of the vibration. When it comes out from this one, that amplitude decreases, and when it reaches in unloaded region, it will become almost negative or minimum value. When again it will enter over here, the that vibration or the amplitude will start increasing from this particular point. When it reaches somewhere here, that point can come somewhere here. When it reaches again here, the maximum amplitude will be there. So based on that equation, which we derived from that one, this particular displacement diagram for this ball has been taken. And based on that one, if I will derive or that FFT of this one, it will give only shaft rotation frequency and cage rotation frequency. No additional BPFI or BPFO are available because there is no defect on race. So this is the vibration response of healthy bearing. Here the vibrations of healthy bearing which we received from experimental data, it is almost same. Shaft FS values, that is frequency of shaft rotation. This is cage rotation frequency were clearly available on in experimentation. When there is a rectangular defect available on inner race of the bearing, we could derive by using that equation, we could find out that these impulses are generated here and that experimental response is like this way. But when we convert on the numerical response and that experimental response in form of frequency response, we can find out ball pass frequency of outer race, ball pass of frequency of outer race. In both the cases, the almost amplitude were almost nearer to each other. So that was verified numerical value for frequency as well as that amplitude available in that case, almost both were same, and the frequency response were also same. So that says that whatever the dynamic model derived was giving the perfect result as per the requirement, and same thing was derived for when there is a defect on outer race, the impulse is generated where numerically found out like this way, and its FFT is given in this particular figure. This is experimental time domain data and its frequency response is given here. So here ball pass frequency of outer race is available. Here second harmonic, third harmonic and fourth harmonic is available. Same thing is available in case of outer race defect. Suppose the dynamic load is given. So in dynamic load, some additional force value P can be added in the equations derived by us in that one. If I am providing this particular additional value of the force, here you can see that the response is disturbed, but even though that BPFO and its harmonics are available in that case, but some additional vibrations will be there. So experimentally, this additional dynamic load was added by means of electromechanical shaker. So that was actual condition available in industry where that actual signal is masked by noise. So here noisy signal is available and we can get better result if we are using some denoising techniques. And this is for circular defect on inner race. Again, same thing, BPFI and BPFI minus FS, BPFI plus FS is available in that case. Now, this particular model can also be useful when more than one defect is available on the race. Suppose there are two defects. Let us say defect A is there, defect B is there on outer race. So there are three possibilities. The angle between two ball is more than the angle between two defect. In this case, the defect angle between two defect is same as the angle between two balls. And here the defect angle is more as compared to the ball angles. So what happens if this is the case? When two defects, that angle is less than this ball angle. So what happens when it start to rotate? As the cage start to rotate, ball number one will come into contact with first defect, and then the same ball will come into contact with second defect because this ball is rotating in this direction. While in this case, both the ball will come into contact with both the defect at the same time. While in this case, the ball one will come into contact with the first defect, while ball second will come into defect with second defect. So the time period of the impulse is generated in three cases will be different. So that can also be modeled based on that angle between them. So this is equation for that when time delay between two defect can be given by the defect angle, and this is the frequency of BPFI. This is angle theta available between two ball. So these equations provide results in case of multiple defects also, which the pictorial view or photographic view is given over here. There are two defects on outer race. Same way, if there are two defects on inner race, then also it can be a different position in case of inner race, because in most of the cases inner race rotates with the shaft. So the time of contact of that defect with the ball will be different at the different speed. So it can be simply given by this particular equation, psi is the angle for defect, and that will provide you the calculation part here, that the time delay between two impulses. So this is the case when two defects were available. The defect angle between two defects or angular difference of two defects were 30 degree. The defect widths were 2 mm. So the time period according to the speed of rotation was 0.0088 seconds. So this is its measured, that vibration measured through accelerometer experimentally. And here also we have derived the things based on the model which we have derived. The time duration were calculated based on the equations derived in the last slides was this one, and same thing was observed when we zoom out this particular thing. So this is the defect when one defect come into contact with the first ball, the second defect will come into contact with the same ball. All the defect second is in contact with the second ball, and defect second is in contact with second ball. So this way that this duration or that time duration of impulse is generated can be achieved from that equations derived from that. But we have noticed that there is not much more difference in its frequency domain. Either it is a single defect or multiple defect. Only the amplitude of the defect will, the amplitude of the vibration will change. There is no change in frequency response. The frequency response for single defect or multiple defect almost remains same. Only its amplitude will change. Now, this model was again that refined by considering some additional damping effect which were neglected in the last model. The damping due to the lubricant were not considered in the last model. So additional, this C2, C3 will provide additional damping available between inner race and ball, damping available between ball and outer race. So elastohydrogen damping have been considered. This is for, this part is the model of shaft and inner race. This part is for mass of ith ball, and stiffness is combined stiffness of ball and inner race, damping coefficient and EHL between ball and inner race. Here this is for mass of housing and outer race, and combined effect of stiffness of ball and outer race, damping coefficient, and this is housing effect. So here I am showing you this was a different case. Here the bearing was kept over here. The same kind of thing is shown here, but additional thing was the elasto-aerodynamic damping part were considered. So equations of motion, this is the additional part which have been added in this case. For balls, also some damping consideration is there here. And it was elasto-hydrodynamic damping. That equations have been derived by Sarangi and all. Then the same equation were implemented in equation. Their approach of dynamic model was different than this one. So by considering this effect of damping, the total A, the stiffness due to that elastodynamic damping have been added into the damping of inner and outer race damping which we derived. Some additional part we have added over here considering that parallel connection between them. And suppose there is a distributed defect, this part is for local defect and this part is for distributed defect generated on outer race waviness, inner race waviness. Experiments were performed both the cases along with numerical results. So this is photographical view of that. So this kind of actual profile, ideal profile should be like this way, but due to that waviness, the actual profile is here. So there is a variation in that. Here this will provide some waviness. All are the photograph for that because that waviness order is changed in this case. Number of waves available in one periphery is 20. Now simulated effect for dry, that means if lubrication is not there, in that case we found out that values are available for healthy bearing was only Fs, 2 Fs, 3 Fs, that is shaft rotational frequency. While simulated lubricated, then in that case the value is decreasing, and that is a proof of that the damping is available in the system. Same way here we can find out simulated data for defective defective rays. Here we can find out defective outer rays for the dry and simulated for lubricated. So in the comparison of this one, it was found out that amplitude of defect frequency were decreased due to the consideration of lubrication, which were also available in its experimental result and lubricated results available with these simulated equations. So the same thing was repeated for outer race defect also. And when there is consideration of waviness, when this kind of waviness is available in that one, we have used the same equation used by Tandon and Chaudhary sir, that outer rays amplitude can be the initial amplitude plus sinusoidal wave of that is consideration of number of waves available in that one, and the outer raceway waviness order which theta j can be calculated by position of the ball. And for inner rays it is almost same kind of things, but here the value will change for MW. So the derived results are like this way, as we have found out that when the waviness order is 1, the principal frequency will be same as Fs, and that is rotational shaft rotational frequency. But if the waviness order is in multiplication of number of balls, suppose one time number of ball, two time number of balls, then frequency, that defect frequency will move like that Q into number of balls into Fs minus Fc. That is shaft rotational frequency, cage rotational frequency. And difference of that is multiplied with number of balls. So the same thing can be noticed over here. If this is the case, that is number of balls into 1 minus 1. 8 balls are there and waviness order we consider was 7. So in that case, the frequency which is given by this equation by available in the literature, same thing we found in both the cases. For simulated result, it is number of balls into difference of shaft rotational frequency, cage rotational frequency minus Fs. Same thing is available in experiment during experimental result also. And when the number of defects are or number of waviness is same as number of balls, almost same kind of things here and here are available for inner race. And if waviness order is increasing, the complicated vibration or frequencies are available. While that higher order waviness is available in the system, it will give some complex result. But still it is verified with experimental results available with us. And same thing has been repeated for outer race also waviness. And we can find out that when waviness order is 20, load acting is 12 kg. So we can find out these peaks at cage frequency into multiplication of number of balls. In both the cases, simulated result as well as on experimental result. And the last part of this one is that we can derive the mathematical model for defective shaft also. This model is derived by one of my PhD students still, that this particular work is under review. And suppose this particular shaft is supported on two bearings having two discs, and suppose unbalance is available on one of the discs, and here there is a defect on the shaft. So the same fundamentals can be implemented here, but in this particular case of the shaft system, that modeling we have done is by using FEA model, because consider that changing of the that change in the unbalance and changing the position of the particular crack, either it can be any element over here, it can be nearer to bearing, it can be near to this particular rotor, or it can be middle of the shaft like that. So this particular model which has been derived includes mass matrix, that damping coefficients and stiffnesses. So here the gyroscopic effect has also been considered. QT, that is in 4 degrees of freedom for each case, in X direction, in Y direction, transverse vibrations, and is torsional vibration theta and sine, that will also measured by using this particular model. This part is used to introduce the crack on that shaft. This part gives that unbalance of the model, unbalance of the disc, and this is the gravitational forces acting on that. And based on this one, this model is capable to find out the effect of breathing crack and what will the effect of breathing and on the natural frequency of bearing rotor system, the effect of position of breathing crack on the dynamic behavior of the shaft, the effect of the depth of breathing crack on the dynamic behavior of the shaft. So here the position and depth, both things can be studied, and the orientation of breathing crack of the shaft. So if there is a crack available on the shaft, so at different sub harmonic speed or at the subcritical speed, when orbit loss displacement on x direction and displacement on the y direction were discussed, and if the crack is available, so when shaft is rotated near to 1/3 of critical speed, these kind of two another circles were available when it is nearer to uh, its 1/3 critical speed, one orbit is available, and when it is above 1/3 critical speed, again two that semicircles were available in this orbit plot. So this is proof of the availability of the crack. If there is no crack, there will be a simple one circle or that circular orbit is available, or it can be a elliptical orbit. And when it is rotated to its 1/2 of critical speed, then another circle is available while it passes through it 1/2 critical speed. When it is below 1/2 critical speed, one inner circle is available. When it is above, then inner circle is available. And when it is nearer to that one, almost one circle is available. So this is the proof of the availability of the crack or breathing crack on the shaft. So this way, here I would like to conclude my session. In this particular session, I have discussed about how can we model that crack in a shaft or in a bearing system, and more precisely, how can we introduce that crack in the model that I have tried to introduce the things. Okay, these are the references. Thank you.
Please, if anybody have any query regarding this lecture, please ask.
Hello.
Any question from audience?
Hello. Any questions?
Any question, please? Any question? Sir, I have a query. Can we use the finite element modeling to solve this vibration problem of rotating shafts?
Yeah, rotating shaft. Yes, yes. Yes. Am I
So
audible?
which element model? Yes, yes.
Yes, yeah. Yes, please.
So you have presented analytical modeling.
Yeah.
So what will be the steps in the finite element simulation?
Yeah. Sorry to tell you, but this paper is under review, so that particular methodology I have not discussed here. It will be available very shortly.
Okay, okay.
So that I have not definitely I would discuss those things, but it is under review, so I cannot give those things so that I have not given. Otherwise,
Okay, okay. Thank you, sir. Thank you.
Otherwise I would give those things.
Okay, thank you, sir. We will discuss in the
Yes,
next
definitely. My email
meeting.
address is with you.
Sure,
So
sure.
as it is available online, you can ask me. I will explain all the things again.
Okay, sure, sir. Thank you, sir.
Yes, any other doubt?
Any other question, doubt?
Yeah, someone has how to solve 6 to 8 differential equations. Someone has written that. Yeah, that more than one differential equation, you have to convert that differential equation, 2 degree of that second order differential equation into single, the first order differential equation. So if there are 6 equations of second order, those things should be converted into 12 first order differential equation. And then by using ODE, you can solve it. Yes, yes, please.
State space formulation. Yes.
Yes. Any other query, please? Any other query, please?
I think there is no question, so we close this session.
Okay, thank you.
Thank you, Professor Vinod and Patel, for
Yeah,
presenting this valuable lecture.
Thank you. Thank you.
Thank
Okay.
you. Thank you.
Can I leave now?
Yes, yes.
Okay, thank you very much.
The other participants are requested to fill the Google form for attendance for this day 2.
Good afternoon, dear participants. We will be sharing a attendance cum feedback link on your WhatsApp group as well as in the chat box. Kindly fill that form within an hour. Okay, because after 1 hour we will be closing the responses for that. So kindly fill it within an hour.
I think email पे भी share कर दो please.
Okay, I'll be sharing via email also.
Okay, okay. Thank you. Thank you.